Hi, and welcome to this video about writing an assembly language program, a very simple one with Visual Studio without having any kind of C or C++ code. So something that is just pure assembly, there is no high-level language involved. Now, such an option doesn't exist in Visual Studio by default. There is no project template to do something like this, but we can still do it if we know what to do. In fact, we can create a template of our own to make that easier the next time around. So there's no project template out of the box to provide that support, but we'll make our own. If you want to learn more about assembly language and the x64 processor, you might want to join a live class in January 2024 if you're seeing that early enough. And if not, there might be other iterations of the same course going forward. So let's go back to our Visual Studio, the trusty Visual Studio, and see how we can get something like this working. So let's go ahead and create a new project. And since we don't have such a project available, in fact, I do have that project available because I already created a template out of it, which I'll show you how to do. Let's start with something that we can fairly easily get to where we want to go. And we'll go with a C++ console application, something very simple. Let's call that something like hello. Maybe hello assembly. Sounds like a good enough name, and use create. So what we get here is the normal stuff Visual Studio provides, which is just this source file with a very simple hello world code here. We have a single source file, and we don't need it really because we're going to do something in assembly. So you can go ahead and just delete it using Solution Explorer, for example. So the first thing to do is to make Visual Studio understand that assembly files are relevant and it knows how to use the MASM assembler, the Microsoft macro assembler, to compile those assembly files. So the way to do that, this is not provided by default, we have to do something, is to right-click the project, go to Build Dependencies, and then go to Build Customizations. And here in this dialog, which always opens way too big, there's the option here to add a MASM set of targets. So it actually provides more information to Visual Studio as to how to work with .asm files, how to compile these or assemble them to be more precise. So there's these internal files with the targets and props extensions that are provided by Visual Studio but not enabled out of the box for C++ projects. So we have to do that, and then we can click OK. Now we're in a better position to add a new item. So we're going to create an item. I'm going to create a C++ file, but it doesn't really matter because I'm going to give it an ASM extension. So let's call that just simply hello.asm. And given that we have this extension, Visual Studio should pick that up. We can verify by right-clicking and go to the properties of this file. You can see that the item type is Microsoft Macro Assembler. So it does pick up the correct tool to use for this particular extension. We can see there's lots of other options here, but without adding that customization option that we did just earlier, you wouldn't see macro assembly here, the Microsoft Macro Assembler, in this list at all. So it just wouldn't work. But now it was added as an optional item type, and it's also picked up by default if you use certain extensions such as ASM. Technically, you can use any extension you want, but in this case, you might need to change the item type to, again, use Microsoft Macro Assembly here. Okay, so that's all good. Let's now write some assembly code. So of course, writing assembly code properly is beyond the scope of what we can cover here. I'm just going to do something as simplest as I possibly can, and that is not too trivial. And so the way we're going to do that is by having these two sections. One of them is code and the other one is data. And what we want to do here is to add or create a little bit of a message box. So let's just in the data section add, say, a caption. And let's give it some text here like hello world. Well, I have GitHub Copilot working here in the background, and sometimes it has good suggestions, sometimes not so much. So let's go with hello assembly here. We'll have a 0 here as a null terminator because the message box function would like to call uses the pointer to the string as a way to display the string and use the string, and a null terminator is required. And then we can also have a message, or let's call that text, and say that this is a nice, well, maybe a nice assembly program. Yes, it could be. And then we're going to use the end instruction here, the directive that tells MASM that we're done with assembling this file. This is necessary because MASM is kind of picky about that. And now we need to write some code. So first we're going to use something like include lib. And this is like importing a library. In this case, we want user32. This is what we want, user32.lib, because that's the one that has the message box function we'd like to use. And now we need to declare this message box function, the existence of that. So I'm going to use message box A, which is the, in fact, the ASCII version, because we use ASCII strings here. Of course, we could use the Unicode versions, but this is just a little bit simpler. And we're going to use the proto directive, saying this is a function. It's also possible, as you can see here, to pass the parameters. In fact, these parameters are wrong, so I'm not going to do that. So just keep that with just proto, and we'll have to pass parameters correctly once we start our code. So again, Copilot here has nice ideas. These are wrong. So let's start with the main procedure. We can create a procedure that's just a function from an assembly perspective. You can call it anything you want. Main seems like a good enough name. And then we need to make the call to message box A. So how do we do that? And the way to do that is to use the call instruction, perhaps, with message box A. And the Copilot here is very nice to try to give us all these parameters, but that doesn't really work. And so we can just call the function. We have to pass parameters based on a calling convention. Since we're going to build that for x64, we're going to use the x64 calling convention, which specifies, at least for our purposes, the simplest thing I can say here is that the first 4 parameters are passed in registers, which are RCX, RDX, R8, and R9 in this order. And luckily enough, we have here, if you look at the message box function, we actually have 4 parameters exactly, so we don't have to pass any further parameters on the stack, which is perhaps slightly more convenient. And again, all the details about that are documented, and of course, I recommend you attend my class in January 2024. Anyway, we have to figure out how to call this function using these parameters. So let's look at the parameters. The first one is a handle to window. This is just the supposed to be the parent window of the message box, if we so desire. Null is also a good option. And so I'm going to zero out the first parameter, which is RCX. And the typical way to zero out things is by using the XOR value with itself. That's a faster and more compact way of zeroing some kind of register instead of just moving a value of 0 into it. So I'm going to zero that out. The second parameter, as again we go to the documentation, says this is supposed to be the text we would like to display, which is available here in this text identifier, this label. And so we need to provide that to RDX. So I'm going to do that using these options. I'm going to do RDX and then the offset in memory of text. I'm not saying it's the best way to go. In fact, it is not, but it is perhaps easier to understand because we're not really talking about full assembly language here, just giving you some basics. And the next parameter is in fact the caption, and in this case, well, Copilot is completely right. So the next argument is passed in R8, so we have the caption here. And lastly, we have the last parameter, which is a type, which essentially means which buttons we would like to see in this message box, and also we can work with some icons. So we're not interested in any special buttons except OK. And so we don't need any special values there, but maybe a nice icon would be nice. So let's grab this MB icon information that has the value 40 hex. Now this is not defined anywhere here, so we'll have to do it ourselves. So we can do something like, well, that was very weird. Let's call that MB icon information. Copy pasting there didn't really work very well. And then it's going to equal 40 hex. So in fact, in this case, Copilot is right. We've seen that indeed the value of icon information here is 40 hex. So good, we have that. So now we need to put that into the last register, which is R9. And again, nice enough from Copilot here to give us that, that thing. So once we do a call, we can use ret that returns from this procedure to somewhere, which is not clear at this point what somewhere that is, but we'll see that once we debug this application. Are we done? Well, not quite. First, we need to do something else here, which is definitely not trivial or not self-explanatory, is really just subtract RSP with 28 hex. That's 40 bytes. Maybe I'll just write 40 here. And this has something to do with the calling convention itself. So we have to provide some memory for the calling function where it's able to spill its arguments if it so desires. So we have 4 arguments, and we always have to provide this space for 4 arguments. Each one is 8 bytes in size for x64, so we have 32 bytes. Then we actually have to add 8 in order to align the stack to 16 bytes. Otherwise, we'll get a crash. And the reason is not, again, perhaps obvious, but trust me, you have to do that, and we'll do that. So once we have that, we need that extra 8 bytes here as well, because, well, actually the reason is that the return value, the return address is stored there on the stack, so it's not aligned when we get into the function. And that's why we have to add another 8 bytes here. And then we're going to do the opposite to keep the stack in check, and we're done in terms of at least the code, at least that's my hope. So let's try it out. Let's build. We can go and press build option here and see what we get. And so apparently something is wrong, but there is no complaint here about the assembly itself. So assembly is probably good. Well, it still might crash at runtime, but at least it's good from a compilation perspective. But something is still wrong because there's a, well, actually, there is a bug here. We have a main proc and we have to end that with the end p directive. So maybe that's perhaps better. So now we get the real error that I was aiming for, and it's not a compilation error, it's actually a linker error. It says, well, there is no main CRT startup anywhere, and so I can't really work with this thing. I can't build an executable out of that. And so the thing is that by default, Visual Studio, the linker is looking for an entry symbol, which by default is main CRT startup for a console application. This is where the C runtime actually starts stuff, initializes stuff in your process, and then calls the real main function that you might write in C or C++. But now we have no such thing in this application. And so the linker is complaining. There's nothing here to get. There's no main here that I can call, so I can't. So what we need to do is to tell the linker that there is no main, or to be more precise, we have to tell the linker we have our own main. So we can go to all configurations here, and if you want, you can also go with all platforms. You have some need to build that with 32 bits, but of course the code would have to change because the calling convention for x86 for 32-bit is different. In fact, there are several of those. But we'll disregard that. So in the linker here, we can go to all options and look for entry point, to make it a bit easier. So the entry point here by default is that one that we've seen as the linker being the one complaining for main CRT startup. And since we didn't call our function, our procedure main CRT startup, we could have, and that would resolve the problem as well, but probably the name main is more appropriate. So let's use main here and click OK. And now we should build successfully, and we do. The last thing to do, which is well, technically optional, but I think it's appropriate here, because we created a console application, what we have here is the console that's going to pop up perhaps, which is inappropriate. We're building a Windows application that has potentially a GUI, and we don't really want the console popping up, so we have to go to the system area here in the linker settings and change the console here to Windows to make it a Windows application, which just means that the NTDLL that runs early in the process lifetime will not create a default console for us. We don't really need it. And then let's rebuild that to make sure that it goes into the executable, and that is it. Let's see if we can run this thing. So we can run it with the debugger or press Ctrl F5. Let's do Ctrl F5, and here's what we get. Hello assembly, this is a noise. Oh, well, I guess that's my bad. I really wanted to write nice, but good enough. So it works. In fact, we can debug this by pressing F5. So for example, I can go ahead and add a breakpoint here just before XOR RCX and go ahead and run with the Visual Studio Debugger by pressing F5 or using this link. So now that we did that, we can see that we're in this location. We can see the call stack, which doesn't look very inviting, but we do see the call stack here. We don't see what is being called here, and that's fine for now. But we'll see perhaps when we want to, we can actually see a little bit more about that. But let's see if we can figure out what's going on by using the watch window here. So in the autos and locals, you'll find nothing. We're talking about registers here. Visual Studio doesn't think that they're worth looking into. So we can put those registers here in the watch window. So here's RCX, RDX, and R8 and R9, which we're going to use. And of course, we can also look at other registers like at RSP, for example. You can see that RSP here has a value that ends with 0 here from a hex perspective, which means that it is 16-byte aligned after we subtracted 40 bytes. I didn't really put a breakpoint before that, but we could have done that and seen the value of RSP if you so desire. So now let's move on by pressing F10 to just advance forward. You can see RCX has been zeroed out as we expect. And then we can put into RDX the value of this this data item, this text here, and it's definitely okay to just grab this and look at this address in a memory window. We can go to Debug, Windows, and look for memory. There are several of those. Let's grab one. It's good enough. Let's paste the address. You can see here that we have the actual text, the actual bytes are shown here. So we can combine the memory window just looking like you can do in a normal C or C++ application. And then we can look at the caption. So we're loading the caption here again, same idea. And then with R9, we're loading 40 hex to provide the support for the icon. And then we can call message box here. So if I just press F10, this is all going to be done. The message box appears here on my other screen. And when I press OK here, you can see it moves to the next line. And now we're fixing up the stack pointer, and we're done essentially. We're returning. Where are we returning? So if I continue to press F10, we can see that in fact we're returning from some startup code in kernel 32 that is being called by some startup code in NTDLL, which is what we expect when there's nothing after. Well, that's always the first two functions for every thread in user mode. And since we don't have any C runtime here, we actually are functioning just like a C runtime in that respect. We're the first thing that's being called after NTDLL is ready to call us. And so we can continue debugging. In fact, if we see any kind of call instruction, we can actually step into that using F11 or step into. We can do that with our own functions or with whatever we see here in the assembly window. So if I press F11, we're now into RTL exit user thread, one of the functions that is being called here to exit the current thread, and so on. And again, we can examine registers here as they change. In fact, they do. And again, we can use here the call instruction. Again, we can step into these anti-query information thread things and see what that does and so on. But this definitely requires more understanding in terms of assembly. So we can end that. Another example that we can use here, just to give you a sense, if I debug this again, I can in fact go ahead and go to Debug Windows and look for this assembly window right here. So you can see the assembly that is generated. Of course, this is not perhaps too surprising for things like sub RSP, 40 or XOR RCX, RCX, but some things might be more interesting to look at. So it's definitely possible to see the actual assembly being generated. And in fact, you can go ahead and if you want to see the actual bytes, you can see there's the option by right-clicking here to show the code bytes. So these are the actual disassembled code bytes that have been assembled and created by MASM when we compiled our application. So it might be interesting for certain cases. And again, you can go ahead here and, for example, I can dive into the message box A call by pressing F11. So we'll see we have a jump here through the import table, and then we're in the actual message box function. And again, we can track registers using the watch window. So hopefully that makes sense. Now, in order to make that easier, well, there's one thing I wanted to show you here. Let me go to the folder in Explorer here. So here's our folder in Explorer, and here's total PE and my PE viewer, but you can use other PE viewers if you so desire. So if I take something like Explorer and drag it here into total PE, we can see that it has many sections, and there's imports here indicating that it has these many dependencies, which of course is fine. One of these dependencies is actually the C++ runtime. That's the DLL right here. In any case, if I go to PE here and disassemble the entry point, you can see the entry point is going to call something that is that's going to be part of what the I would say the C runtime is providing as initial, I would say, infrastructure for the process before we actually get to the main function, which is in a different location. We can of course continue here by right-clicking this address and disassemble at the end to see more of the code here that is being invoked and so on. It's not perhaps the most convenient way to explore assembly in an executable, but this is a work in progress, obviously. So that's Explorer, but let's look at our application here. So let me grab our application here. So we have this hello assembly, and here's x64 debug. That's our executable. Let me drag that to total PE. So what we find here in total PE is that we have these sections, as we might expect. They're actually much smaller than in the Explorer case. Obviously, there's not a lot of code here. In terms of imports, we only depend on one thing, which is user32. This is the imported DLL that we need to use because we call the message box A function, as you can see here. That's the only thing we did. Now, if we go and disassemble the entry point, we can see that basically what we have here is our code. So you can see here there's a jump here to this location here. That's the address 410 that's generated by the assembler. And this is of course not optimized, but easy to track. So we have the sub RSP, here's our values in those registers, and then we're calling this function, which is supposed to be the import table address for calling message box A and so on, and we're done and calling ret. And the actual values are in a different location. In this location 14000, well, with that 10 at the end, we should find them somewhere maybe in the data here. And indeed, you can see the strings are in a different location because the linker just arranges the sections. They're not really contiguous. They can be in different locations. They have to be at least on page granularities or in different locations, but they're here. You can see the data does exist, and this is what is being pointed to by these instructions. Just to give you a sense of the final result. Now, the last thing I want to show you is how to take this, say, example application and turn it into a template. So now you can use File New Project to already get all these settings, such as adding the customization to support MASM, and to make the entry point use the name main, say, and change the subsystem to Windows. So the way to do that, once you have a project of your liking, and you might want to make that a little more, well, less verbose, maybe something more minimal. Anyway, you can go to project here and you can do export template. When you export template, you can select the project template, which is what we want. We want the entire project to be part of a template. We can use next here. You can give the template a name of your choosing, and then some description if you so desire. You can have an icon here and a preview image, and it's going to do everything for you once you click finish. Since I've done that already, I already have such a template. So if I go to new project, that template can be searched based on its name. It's currently in my pinned templates here called the low ASM. That's the name I provided to it, and also added a nice icon as part of me creating that template. And now if I do that, like select something like this and maybe change the project name, we get some minimal code that I've used. In this case, it's something simpler than message box. It simply calls the exit process, and that's it. This is a function that never returns because it causes the process to exit. But we have all the correct settings for the linker so that we can build these things successfully. And of course, now we can change the code to anything else we desire. So once you have this template working for you, you can reuse that, which is very useful if you want to continue experimenting with this kind of thing. But of course, creating templates out of projects is a generic thing that you might want to try out. So that's it. I will post the code as usual to my GitHub repository and also have this link available in a comment. Thank you for watching.